Greetings and welcome to the Artifact Electronics channel. Today we'll be looking at this Hewlett Packard 3585A spectrum analyzer covering a frequency range from 20 Hz through 40 MHz. I bought this through eBay. It was advertised as non-functional. The only thing that does happen when power is applied is that the overload light shines rather faintly, and that's all. There's no fan, there's no beeps, there's no screen, nothing happens. The description was very accurate. It was described as being in good shape physically, which is also true. So we'll probably start by looking at the power supply. Now before going there, a little bit of background on this type of device. It was built, or they started to sell this in 1978, and it had a retail price of $26,000 US. To put things into perspective, at the same era, a Moog Mini Moog synthesizer went for $1,600. A Ford Pinto, marvel of automotive engineering, went for $3,000. And a Mercedes-Benz 450 SL convertible went for $27,000. I'm sure that if you had that kind of cash at the time, it would have been a very difficult decision whether you would buy the spectrum analyzer or the car. But with that said, you did get your money's worth with this. It weighed in at 88 pounds dry and 100 pounds wet, and by wet I mean in the factory packaging. It is very heavy and unwieldy, so it would have been nice to have a forklift here, but I don't, so I had to manhandle it, and it is not a joy to move around. But maybe we can cause some joy to getting this thing to do something. So let's go ahead with disassembly. Here's the back. It's got the AC input, GPIB input, some transistors mounted here using the back panel for heat sinking purposes, bunch of I/O here. It does have an internal 10 MHz oven reference, which is connected to the, this is the output of the internal reference, and this is the input to the device's reference, and it's connected with this, but this allows you that if you feel that the internal reference is not accurate enough, then you remove this bridge connector and you plug in your own reference over here. Now to get off the back, I have a few screws to remove, and let's see what's underneath there. Here it is with the back removed, and what we can see here is the initial stages of what's happening with the transformer. And if we look at this, we can see here's all of our secondary tabs. There's two bridges, which are here and here, generating 50 volts DC, and some protection circuitry over here, which is also located here. And I did turn on power and check the bridge outputs, and there is plus minus 50 volts there, so our problems are a little bit deeper. One thing I wanted to say before moving on: if you're going to buy one of these, make sure that this little connector is available, because, you know, as I said before, it basically connects the internal oven reference to the 10 meg input, and you don't want to be using a long BNC cable on this, or even a short BNC cable. You want to take the shortest path possible, and that is this connector. And I've seen another one or two of these for sale, and one of them didn't have this. So that's one thing to watch out for when buying one of these. But let's go further ahead and have a look. Going back to the schematic here, we basically see that there's several secondary voltages being fed out. They're further rectified here, and we start to get some regulated voltages here. Plus minus 24 volts is generated here, and that is generated on a board inside that looks like this. And what I'm going to do now is find where the output of these bridges go to, hopefully find this board, and to continue our troubleshooting. I took off the top cover. We're looking at the top of the instrument here. Sea of connectors, everything nicely gold-plated. But all the necessary voltages are generated in this card cage over here, and there's cards for all of the necessary voltages. So let's take off the little cover and have a look inside to see what, if anything, is happening. They do have little holes, little access holes here where you can do voltage checks or voltage adjustments. And I checked the first card over here. It looks like the bridges are connected to the very first card over here, and there was a few millivolts coming out. Let's have a look there. So in order to gain access, we got to take off the cover and go inside. Here's a little closer detail. It turns out that each one of these boards, not this one, but all the following boards, have status LEDs on them. A green and an orangish LED, and when I previously powered it up, either both LEDs were off on all of these, and on some of them the orange LED was on, which by looking at the service manual indicate a malfunction, or that there is something in here that is drawing too much power from the respective voltage, loading it down. But let's start with the one that's generating the 24 volts, and I always try to be careful so as not to break the tabs on these, and they don't want to come out, so let me loosen things a little bit off camera, and then we'll continue. Well, as it turns out, there was a lock bar across the top of all of these cards, which I removed, and then it let me easily use the tabs to loosen the board and pull it out and not drop it. So here's the board, and it is the board that we saw in a previous illustration that generates several voltages or for the rest of the instrument. Now, unfortunately, I don't have this on a video, but remember, I had the unit powered up for a while when I was checking the bridges on the back of it, so all of these boards were getting fed power of some sort. And as I pulled the board out and grabbed it to lay it on here, I belatedly realized that this heatsink was extremely hot. And the reason I'm saying too bad I don't have it on video, I'm sure some of you would gotten a rise out of my reaction to when I found out that this was really hot. But anyway, it was also a good thing because it is pointing me in the right direction here. Briefly as to the function of this, it generates the plus minus 24 volts. Hint, hint. It also generates plus minus 5 volts and 150 volts that is used by the CRT. The CRT derives all of its voltages from the 150 volts. There's a fuse for the 150 volt line, which was good. Here's some more bridges for the 5 volts, pass transistors, and other related stuff. But let's get down to the suspects here. Looking at the schematics, the suspects are the pass transistors for the 24 volt supply, and another component on that heatsink is a thermal switch that I am sure tripped and shut off the 5 volt supply when the temperature started to rise. And what I'm talking about is this guy. It's a thermal switch. It's a passive device, so that's not going to heat up the heatsink, but rather one of these two is. And so I proceeded to remove these two, and be aware that I already had my soldering iron warmed up, but it turns out they use single pins onboard sockets, so all it takes to remove these is remove the mounting screws and they slide right out. I measured both of them out of circuit, already starting to make up a new mail order to get replacement transistors when I found that both of these were good. So the problem lies somewhere else, because when I put them back in and I measured them, they showed a short on the base. This one showed a short on the base emitter junction, so it had to be something else in the circuit. There isn't really that much, but as luck would have it, I probably measured and removed everything else that I got a bad reading off, and saw that all the diodes were good, everything was good, but drum roll please, it turned out that this bypass cap over here was shorted, was completely shorted. Now normally capacitors are nice, they'll open up, but this one decided to short and essentially make these guys heat up, which tripped the thermal switch and shut off the 5 volts, but the thermal switch does not shut off these guys. So they were happily trying to supply amps and amps of current and heating up the heatsink, and surprisingly they didn't self-destruct. The capacitor in question was this one, and it had its partner here that worked for the negative 24 volts, and this is what they looked like. So here's a capacitor that used to sit in this spot. So I'll get up to the meter, and let's measure its capacitance, and it's measuring 0 microfarads. I mean, this is what the meter looks like when nothing's connected, and when you connect this, it does measure the 0 microfarads, which is obviously bad. We can go to the next, we can just go to the continuity test setting. They'll show 1.6 ohms, I guess that's the ESR at DC, which is a very bad thing. But the long and the short of it is, this guy is bad and was causing this thing to heat up. Now, its brother was installed right next to it, and even though that guy tested good, they are coming from the same place. So since it was open, I decided to replace both of them. The other thing I noticed was that we had the bypass cap for the 150 volts, and you can see around where the lead exits the capacitor, it was starting to turn dark, which looked like some sort of leakage or whatever. The cap tested good out of circuit, but since I was at it, I replaced it. And then it was basically time to put it back in and see and somehow monitor, well, we could measure the output voltage, but somehow monitor the heat, the temperature of the heatsink to see if that in fact repaired the problem. So it's time to put the card back in and see what happens. The way I'm planning on testing this is I have a cheap OIR thermometer, which is surprisingly accurate. And what I want to do is basically point it at the heatsink, power this thing up, point it at the heatsink, so I can shut this thing off immediately if the temperature rises dramatically. I'm going to plug in power, but before I do that, it's the obligatory please be safe when you're dealing with things like this, especially in this case. When I plug in AC over here, there's going to be live AC over here. Well, live AC back here. There's high voltages here. Don't hurt yourself. Keep your hands away from it and always follow proper safety procedures when doing anything like this. So we'll plug in the power. Get the thermometer ready and hit the power switch. And the fan started running and it beeped. And it looks like there's a bunch of green lights on. Let's see if we can zoom in on those. And green here, green here, green here, green over here, and green over here. Well, I didn't even use a thermometer. I just want to see if there was smoke coming out of there, but it isn't. And with all the green lights on, we've definitely fixed something. So let's have a look at the front of the instrument. Here's the instrument turned around. I'm being slightly pessimistic. That's why I've left off the top cover. But it's plugged in. And we already know that the fan's going to run and that's going to beep, but let's see if the screen does anything. Well, it says it's sweeping, and we get a display with a nice noise floor over here. And well, let's see if it let's see what it does with the signal. But before doing that, I need to show you some more detail of the inside, at least the top of it, because I think this piece is a work of art, and I do want to share a view of this a little bit more in depth with you. But before we go on to functional testing, let's have another look at the inside of this beast. It was just beautifully laid out. Remember, we had the power supply cage, card cage over here. And it's interesting because the service manual doesn't call it power supply, but rather, more appropriately, power control. And next to it are the digital circuits. They are in their own card cage over here. And of course, finally, we have the analog circuitry over here, which is, all the nice gold-plated connectors connecting everything together. a boatload of adjustments available through the top, not necessitating you to remove the modules for adjustment purposes. And of course, the CRT and the CRT driver over here, proper covers on everything. I just really appreciate this kind of workmanship, and I guess you get what you pay for. Now, if you like looking at well-built equipment like this, I'd like to suggest you do Google search for early high-watt guitar tube amplifiers. Those are wired to mil spec, and no gold connectors or card cages in those. But you should still have a look at them because they are absolutely beautiful. So let's go on and see if it's not just beautiful, but can actually function properly also. Now let's see how she really works. We've already seen that the screen works and that it displays something, but we will need to inject an actual signal to see how well it interprets and processes that signal. Now before that, let me say a word about the internal condition of this. We looked at it, it looked good and all of that. The external condition of it is very good for an instrument of its age and of its weight, because something this heavy usually gets banged up pretty badly when moved around. This looks like it wasn't moved around a whole lot, and I also think because of the quality of the screen display is that this must have died relatively early in its life cycle, and they didn't bother to fix it. And it probably spent 10 or 15 years in a closet somewhere till it finally got taken out and sold and ended up in my hands. Now, sitting that long in a closet, a percentage, probably a good percentage of all the electrolytic capacitors in here are going to drift. With different, the drifts are going to be different and unpredictable. So what I'm getting at is that to do this properly, we would have to go in and do a manual calibration of it. But I'm not going to do that right now, but I'm just bringing this up because our results are going to be somewhat falsified because of the lack of calibration. Second of all, the function generator I'm going to use is also out of calibration, so the cumulative error, resulting error that we get is also going to affect the signals that we see. But with that in mind, let's go and give it a signal. Let's now try a real signal. I'm going to start off with a 1 kilohertz sine wave. And the reason I'm using a low frequency like that is because for my own uses I will mostly be using the spectrum analyzer to analyze audio type signals, and for that 1 kilohertz is appropriate. Now again, I'm going to have both the spectrum analyzer and the function generator on, so the fans we're going to hear two fans in the background, but I'll try to speak up and make sure to listen to the video before I release it, to make sure that you can actually hear what I'm babbling about. But first, let's see what sort of sound levels we are dealing with. And for that, I'm going to use this Radio Shack sound level meter. It is picking up my voice and saying that I'm babbling at about 64 dB. And when I shut up, it drops and says low. Low on this one means that the level has dropped below 15 dBA. And so we'll put it here, and then we'll have a look and see what it goes to with both instruments turned on. So let's turn on the function generator and this guy and measure in front of the instrument. So it's pretty level at 61 dBA. My voice is obviously 7 dB louder than that. But I guess the nature of ambient white noise, at least to me, makes it sound a lot louder and more annoying than my own voice. So you may or may not agree with that, but that's the way it is. So now we know how loud these guys are. So let's go dial in 1 kilohertz. We have 1 kilohertz at an amplitude of 1 volt and a symmetry of 50%. We now have to go ahead and set up the frequencies on the spectrum analyzer. So the lower frequency, since we're at 1 kilohertz, let's make that 500 hertz. And the upper frequency, pick a number, 8 kilohertz. Stop frequency 8 kilohertz. And there's our signal. We do see some sideband information here. And of course noise coming up every so often. But the sidebands are pretty constant. And that probably has something to do with the rise time being dampened by the cable I'm using, or whatever other environmental factors there are here, not letting the signal come through cleanly. But in general, that's a pretty good result. We can see the fundamental and little else, I should say. Let's just make sure that the fundamental is correct. If you look at the right size of the rising edge of the fundamental part, you'll see the marker on there. And I'm just going to place it on top. And we will see that the frequency there is 1 kilohertz. So if anything, it measures the frequency correctly. And so now let's go for something a little bit more exciting. One thing I noticed was the device came up, it is set to 50 ohms input, 50 ohm input impedance. I can switch that's off camera, I'm just hitting a button that now switches the input impedance to 75 ohms. And it does change things a little, well, it changed it a little bit on the transition and came up with the calibration warning, but in general, the magic number is 1 megahertz. Anything under 1 megahertz, you can't really tell the difference between 50 and 75 megahertz, 50 and 75 ohm line impedance. And once things stabilize here, it looks just like before, and there's no real difference in the signal display. But let's switch to a square wave. On a square wave, we know we should see all of the harmonics, but looking at the divisions and how far the peaks are, I can already tell that we are missing some harmonics. And again, our marker is still on the fundamental, saying it's 1 kilohertz. Now if we move the marker to the next peak, we'll see that that's at 3 kilohertz, and it looks like we're missing all of the odd harmonics. So basically, if I move the marker down here into the trough somewhere, this is where we should be seeing a harmonic, but we're not. What I suspect is happening is that the symmetry on the function generator is off. It is displaying 50% right now, or since this is a square wave, a 50% duty cycle. And what I'm going to do is bump that up a little bit and see if we get more into square wave territory. I'm going to bump it from 50% to 54%, and we can see that all of the harmonics appear now. We can double check it. Well, our marker even is still on top of the first peak over here, and it's saying that it's at 2 kilohertz. So everything seems well with the low frequency test. I'm now going to change the input frequency to 1 megahertz, test the upper end a little more, and So let's go to a sine wave at 1 megahertz, and we need to readjust the frequency limits of the display window. So let's put the lower limit at 500 kilohertz and the upper limit at 8 megahertz. And there's our signal. Now, obviously, the function generator is going to, because it is out of calibration, is going to start getting inaccurate. And I think the result of this is we're seeing a lot of sidebands here. And I think that's the result of the rise times having slowed down at the higher frequency, causing those sidebands. Now, one thing to check is the symmetry, which is still set to 54% from our last square wave test. And if I turn this down to 50, things shift around, but the sidebands remain. But we still have a clear fundamental frequency over here. And the fundamental is at 1 megahertz. Now we'll switch over to a square wave at 1 megahertz. And see a bunch of sidebands. Change the duty cycle to 54% to get the same conditions we had before. This time all the sidebands showed up, but going to 54% duty cycle evened out the amplitudes a little bit. And they're all there. And just for grins, let's measure the first harmonic. And the first harmonic doesn't want to stay there. Is at 2 megahertz. So I think with all the circumstances being taken into account, the spectrum analyzer is working pretty well. And I think I'm going to give it an initial clean bill of health for now. So I would say here with the repair is officially over. Things seem to work. It's a nice instrument and nice shape. It's a true electronic antique. And being an antique, of course, its functionality is limited. Its usefulness is limited. But it's still something I'm very happy to have and will keep around. If I want to make more accurate measurements, I'll probably go out and buy a PC-based spectrum analyzer that will cost me a couple $100 and will give me more accurate results, such as for products I'm working on. But this is still a nice device to have around. I hope you liked what you saw. If you've lasted this long and you're still watching, I mean, there must have been something interesting in here. So make sure to go ahead and subscribe to my channel, and so you won't miss any of the future wild and interesting repairs and the demos I'll be doing. And of course, if you like it, click the like button too. I'll see you later.